So now that we've begun to get a handle on linear modeling, let's take things one step further. In the previous tutorials, we discussed how to build a linear model where your predictor variable is in the form of categories, specifically two different categories. One step beyond that, then, is a predictor variable that has more than just two categories, and you're interested in how these different categories of the predictor impact the response variable, which in this case is continuous. So in order to build a model with multiple kind of categories in the predictor variable, let's start off by loading in our trusty ArcData package. And specifically, let's use the Barmos1 data set that we did last time. This is a data set of spatial coordinates for a bunch of different artifact types. Now let's subset our data using indexing. So we're going to say within the Barmos1 PP data frame, let's pull out three different artifact types. These artifact types will be microburins, flake axes, and denticulated/notched pieces. And so here what I'm doing is, let me clean this up a little bit so you can see it better, is indexing within the Barmos1 data frame here based on different values from the label column. So Barmos1 label equals denticulated or notched pieces. Put a comma there. So here, what this code is saying is within the Barmos1 data frame, I open brackets, that means I'm indexing within it. Give me all the rows for which the label column has a value of microburins, flake axes, or denticulated notched pieces, and then I put a comma and a space here, basically saying give me all of the columns of this data frame. So here you can see that I've got a space after the comma. If I run this, now I've got this nice subset of the Barmos data set with just denticulated notched pieces, flake axes, and microburins in it. And with this, let's plot the spatial coordinates. As I've said, it's always a good idea to plot your data before you model it so that you better understand what you're dealing with. And so here let's plot the actual spatial coordinates for these different artifact types. Here I'm saying, okay, plot the northern coordinates as a function of the eastern coordinates, so north on the y-axis, x, and then east on the x-axis. Pull those values from the barm data object, which is the subset we just made of three different artifact types. And here I'm adding another argument, the color argument, which in this case I've set to color equals label. Now, of course, label isn't a color, but what R will interpret this as is that I want three different colors for each of the three different values in the label column. So I know that this label column will take either the value of microburins, flake axes, or DN pieces. By saying color equals label, R will assign three different colors to those three different artifact types and plot them as such. So we've got kind of a light greenish blue, a solidly blue, and then a black points for these three different colors. So we can kind of see the different spatial distributions of these three artifact types. Tough to see what's going on here. It looks like the blue and the black are kind of on top of each other, but this kind of lighter greenish blue is a little bit off to the left. It's a little bit more lower values on the easting axis. So let's make another plot of that. In this model, as before, we're going to be concerned with easting values. So let's plot the easting values as a function of label from this barm data subset that we've got. If we run this, we're going to get a series of box plots. Now, because of the fact that we're indexing, R still remembers that there were other artifact types in this Barmos data set, so it's got them still on the x-axis, but it's only plotted the 3 for which we saved the values. So you can kind of see the microburins here, this very tight box plot. This one with a lot of variance would be the flake axes. And then over here you've got the denticulated and notched pieces. So it looks like the flake axes might be a bit different from the other 2 groups in terms of their easting coordinates. So now that we've visualized the data, and we kind of understand, we have some ideas about what might be happening, now we can actually build a model. Let's call it barmmod. Use the lm function as before, and we're interested in modeling easting coordinates as a function of label. Tell it where to find this data, and then we can build that model. So this is going to say easting as a function of label. Label is our category with the 3 different artifact types. Now, of course, before we interpret the model, we need to inspect the diagnostic plots. Always inspect your model's diagnostics. It's not going to do you any good to start interpreting things and then you go and realize that your model is violating a bunch of assumptions and those interpretations are not actually valid. So before we do anything with the model, let's interpret the diagnostic plots. Plot the model object and then go down to the R console and hit enter to see the 4 different plots. The first one is just the residuals, and again we're looking for any weird patterning, but in this case it looks pretty good. It looks like the central tendencies of the residuals for this group are a little bit below 0, and same for the last group, even though the middle group is kind of spot on 0. But this isn't bad. This isn't deviating in any extreme way from what we would expect. There's no other weird patterning in these residuals, no weird clusters or anything. They're spread out pretty uniformly, evenly around that value of 0 for all the fitted values. So let's check out the next plot. This one, the QQ plot, again, that diagonal dotted line is a representation of normality, of a normal distribution of the standardized residuals. And in this case, this QQ plot is actually telling us that our residuals are deviating a bit from normality. Again, most of them are fine at lower values and middle values. Most points are right along that line, what we'd expect if they were normally distributed. But at higher values, at higher quantiles, we're starting to get away from that line. This could be problematic, but I do know that linear modeling in this sense is pretty robust to violations of this assumption. If you remember from before in our lecture on linear modeling and discussion of linear modeling, of the 6 assumptions, the most important ones are first that the model just makes logical sense, that it reflects what could actually be happening in the real world. That's the most important consideration. The second most important is that your model terms are actually additive, that you're not doing any weird math to make your model other than just adding terms sequentially. And then the third most important one is linearity, that your model is not curving in all sorts of weird ways, and we'd be able to spot that in the residual plots. After that, linear models are kind of robust to a lot of things. Independence of errors is important as well, but when it gets down to homoscedasticity or heteroscedasticity and the normality of the residuals, we can handle slight deviations. In this case, looking at deviation from normally distributed residuals, it's not as bad as it could be, and I know that this type of model is pretty robust to this, so we're going to proceed as is. But there are some other considerations that we can discuss in a later tutorial for how to handle some issues when you start really violating the assumptions of linear modeling. But this looks okay for now. In this next plot, then, we've got the standardized residuals square root transformed, and it doesn't look like there's any extreme heteroscedasticity here. The residuals are more or less horizontally kind of on the same axis. It dips down a bit and then goes back up, but this isn't egregious. That's still okay. And then the final plot of Cook's distance. We don't even see the confidence intervals for the Cook's distance measures, which means that all of our data points are well kind of within the range of what's reasonable. None of them are any extreme outliers that are really influencing the model. So the model diagnostics in this case look pretty good. And so since we're not egregiously violating assumptions of the linear model, we can then move on to actually interpreting our model.